Today, we will continue to explore the fundamental principle of mechanics, Newton's second law, which states that the force exerted on an object is equal to the object's mass and acceleration. Based on this principle, other formulas can be derived, which can be used to help describe the motion that we see in our everyday lives. The experiment I conducted videos, tracks, and plots the motion of a falling object, in my case a tennis ball. Unlike the object in the previous experiment, which moved at a near constant velocity, the tennis ball accelerates as time progresses. According to Newton's second, because the tennis ball experiences a change in velocity, it experiences a net force. More specifically, it experiences the force of weight, pulling in the negative y direction, and the force of drag, pulling in the positive y direction. First, I will display the video of the object as its falling motion is tracked on tracker. Afterwards, I will compare the distance versus time plot of the object's observed motion to that of two computational models, one that only takes into consideration the weight force, and one that takes into consideration both the weight force and the drag force. Ultimately, we will see the effects of drag on an object's motion and be able to conclude that the drag force increases as the speed of the falling object increases, and makes a considerable impact on the amount of time it takes for the object to reach the ground. Here is the video of the falling tennis ball. The video was recorded at 30 frames per second, and the diameter of the tennis ball was used to calibrate the length scales of the video. The origin was chosen at the center of the tennis ball, right before it was dropped. The y-axis was aligned such that the object moved in the negative y direction as it fell. The ball's center of mass is identified at each frame, which thus helps tracker to chart the ball's change in position. In many points, the object was blurred, and I marked the center of the blur as the best estimate for the center of mass. Now onto the computer model. First, let's lay out our initial conditions. The ball's mass, which is measured in kilograms, which we will soon see has an impact on the motion of the ball given that the ball exerts a non-zero net force. The ball's initial position, which we specified on tracker that the origin is at the center of the ball before it is dropped, thus the initial position is 0. Then we have the ball's initial velocity, which is 0 considering that the ball starts from rest at time equals 0 seconds. Now let's consider the while loop. Unlike the first experiment, the computer model in this experiment will take into consideration two forces that constitute the net force on the object, the weight force and the drag force. The weight can be identified as the magnitude of the mass multiplied by the acceleration due to gravity and the vector of the force, j hat. The drag force, on the other hand, is a little bit trickier to identify because the proportionality constant b is based on the shape and size of the object and thus must be derived, in this case empirically. By experiment with different values of b, I decided that b equals 0.051 Newton seconds per meter is the most plausible value of b given that the final displacement computed matches the final displacement observed on tracker to the hundredths place. For the first model, we are going to see how the computational model predicts the ball's motion without considering the drag force. To do this, I will set the proportionality constant b equal to 0. Here is the model of the predicted motion of the tennis ball, only taking into consideration the weight force, pulling in the negative y direction. Note that the magnitude of the final displacement is greater than that which is noted on tracker. Now here is the model of the predicted motion of the tennis ball after the proportionality constant was set back to 0.051 Newton seconds per meter, thus allowing the computational model to take into consideration drag as a component of the net force, noted as the blue arrow pulling the ball in the positive y direction. Note here that the final displacement now matches that which was noted on tracker to the hundredths place. Now we will move to compare the three models, that of the observed motion and the two computational models created on VIDLE. To do so, I plot the data points from tracker and the two computational models on a Google Excel sheet. Off the bat, we can note that the computational model without drag is predicted to accelerate at a negative y direction at a higher rate than the model with drag. Because the model without drag overestimates the magnitude of the velocity, the predicted final displacement is larger than that of the observed motion. Comparing the model of the observed motion against the computational model considering both drag and weight, it is important to note that the beginning and the end of the displacements are fixed such that they would match with the observed position. Only the middle portion really predicts the motion of the falling object, and although the model with drag matches up pretty well to the observed position, there are discrepancies and it's important that we consider potential reasons why. The most plausible cause for discrepancy lies in the fact that the movement of the tennis ball was difficult to track on tracker, because the motion of the ball was blurred on each frame, making it difficult to estimate the center of the ball. Beyond that, maybe other models of drag would be more precise in predicting the drag force. For instance, the other method displayed in the lecture video sets the drag force equal to the proportionality constant multiplied by the ball's velocity. Now onto the what does it mean question. Terminal velocity, as described by hyperphysics.edu, is the point at which an object reaches a constant velocity when falling because the drag force equals weight force. A skydiver, for instance, will initially speed down due to the gravitational force. However, because the upward air resistance increases with speed, he or she will reach a terminal velocity where the air resistance force and the gravitational force are equal. Thus, the skydiver falls with a constant velocity known as terminal velocity. To see whether the model reaches terminal velocity, we set the weight force equal to the drag force and check whether the values of the ball's velocity can result in the two forces equaling each other. The first computational model, which doesn't take into consideration the drag force, cannot reach terminal velocity because there is no force resisting the downward force of the weight force. The second computational model, however, probably did not reach terminal velocity because the time frame upon which the video was recorded was short. This is proven by the fact that the length of the area representing the drag force was not equal to that of the weight force in the time frame. Finally, we come to the what-if question. I set my initial velocity such that it starts at -2 meters per second in the y direction. As we see by the diagram, however, that this does not change the length of the arrows for the drag force and the weight force. The two are still not equal in the time frame. Thus, we can conclude the terminal velocity does not change. With that, I conclude my report for the day. Hope you've gained a clearer understanding of the application of Newton's second law as the foundation of mechanics.